Dear guests, dear colleagues and students, ladies and gentlemen, it's really an honor for me to have the opportunity to give a speech at FC 2020. My name is Chong and I'm a professor at the School of Computer Science and Engineering, Northeastern University, China. My research interests include multimedia security and computer vision. The title of my speech today is Image Encryption Technique Based on Chaos. Recent years have seen a fantastic amount of images transmitted over the internet, raising lots of privacy concerns. Encryption is, so far, the best way to keep data secure. Block ciphers, for example, DES, AES, and IDEA, the most commonly used symmetric ciphers, provide a high level of security, but can hardly satisfy the growing demand for real-time communications when dealing with the image data characterized by large volume. To meet this challenge, a variety of image encryption techniques have been suggested. Among them, the chaos-based technique have been proven to be the most successful. Before introducing the concept of chaos, let's first think about the question. Is there a system which is deterministic but unpredictable? Pierre-Simon Laplace, French mathematician and astronomer, who is remembered as one of the greatest scientists of all time, had given an answer that is now known as the Laplace theorem. He claimed that if someone knows the precise location and momentum of every atom in the universe, their past and future values for any given time are entailed. They can be calculated from the laws of classical mechanics. Laplace determinism gained popularity among scientists and philosophers until the late 1800s. Physicists, astronomers, and mathematicians started encountering seemingly unsolvable problems that Newtonian mechanics couldn't help with. The infamous math challenge called three-body problem is an illustration of the limits of determinism. In 1890, Henri Poincaré, one of France's greatest mathematicians and theoretical physicists, found a sensitive dependence on initial conditions in a particular case of the three-body problem. This serendipitous discovery, born from a mistake, led it directly to what we now know as chaos theory. It was the first indication that 3 is the minimum threshold for chaotic behavior. Now let's see the definition of chaos theory. Chaos theory is the study of how systems that follow simple, straightforward, deterministic laws can exhibit very complicated and seemingly random long-term behavior. A classic example of this is the weather. Individual molecules of air all conform to basic laws of physics, but global weather patterns are anything but simple. The story of the discovery of chaos theory sounds interesting. An earlier pioneer of the chaos theory was Edward Lorenz, whose interest in chaos came about accidentally through his work on weather prediction in 1961. Lorenz was using a simple digital computer to run his weather simulation. His program used 12 recursive equations to simulate rudimentary aspects of weather. He wanted to see a sequence of data again and To save time, he started the simulation in the middle of its course. He was able to do this by entering a printout of the data corresponding to conditions in the middle of his simulation, which he had calculated last time. To his surprise, the weather that the machine began to predict was completely different from the weather calculated before. Lawrence checked this down to the computer printout. The computer worked with 6-digit precision, but the printout rounded the variables off to a 3-digit number, so a value like 0.506127 was printed as 0.506. This difference is tiny, and the consensus at the time would have been that it should have had practically no effect. However, Lawrence had discovered that small changes in initial conditions produced large changes in the long-term outcome. In 1963, Lawrence published a theoretical study of this effect in a well-known paper called Deterministic Non-Periodic Flow in Journal of the Atmospheric Sciences, and with it, the foundation of chaos theory. He states in that paper, two states differing by imperceptible amounts may eventually evolve into considerably different states. In view of the inevitable inaccuracy and incompleteness of weather observations, precise very long-range forecasting would seem to be non-existent. Lawrence remarked that if the theory were correct, one flap of a butterfly's wings could change the course of weather forever. According to Lawrence, when he failed to provide a title for a talk he was to present at the 139th meeting of the American Association for the Advancement of Science in 1972, the chair concocted "Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?" as a title. Note that the butterfly doesn't power or directly create the tornado. The flap of the wings is a part of the initial conditions. The flapping wing represents a small change in the initial condition of the system, which causes a chain of events, leading to large-scale alternations of events. In 1963, Edward Lawrence developed a simplified mathematical model for atmospheric convection. The model is a system of three ordinary differential equations, now known as the Lorentz equations. Here x, y, and z make up the system state, t is time, and sigma, rho, beta are the system parameters. From a technical standpoint, the Lorentz system is nonlinear, three-dimensional, and deterministic. When rho equals 28, sigma equals 10, and beta equals 8/3, the Lorentz system has chaotic solutions. The set of chaotic solutions make up the Lorentz attractor, which is shown in the upper left figure. The projections of the attractor on xy plane, yz plane, and xz plane are shown in other three figures, respectively. Maybe someone will ask how this attractor is plotted. The equations can be rolled using rank-Coulter fourth-order method. The above figures are plotted using MATLAB, and this is the source code. You can also use other programming languages like Python to do that. We may now briefly summarize the properties of chaos. The first one is sensitivity to initial conditions. Each point in a chaotic system is arbitrarily closely approximated by other points with significantly different future trajectories. These figures show three time segments of the three-dimensional evolution of two trajectories, one in blue and the other in yellow, in the Lorentz attractor starting at two initial points that differ only by 10 to the power of -5 in the x coordinate. Initially, the two trajectories seem coincident, but after some time, the divergence is obvious. The second one is topological mixing. It means that the system will evolve over time so that any given region or open site of its phase space will eventually overlap with any other given region. The third one is density of period orbits. It means that every point in the space is approached arbitrarily closely by periodic orbits. Following the pioneering work of Lorentz, a number of continuous chaotic systems with new topological structures have been constructed. Let's see two typical ones. The first is a Rosler system, a system of three nonlinear ordinary differential equations originally studied by Otto Rosler in 1976. The leftmost figure shows the Rosler attractor, whose projections on xy plane, yz plane, and xz plane are shown in other three figures, respectively. The second is Chen system, a three-dimensional autonomous chaotic system constructed by Guanrong Chen in 1999 with the method derived from engineering feedback control. The Chen attractor resembles some familiar features from both the Lorentz and the Rosler attractors. The leftmost figure shows the Chen attractor, whose projections on xy plane, yz plane, and xz plane are shown in other three figures, respectively. Now let's look at another type of chaotic system, discrete time chaotic system. The first and the most celebrated one is the logistic map, which is presented by Robert May in 1976. The logistic map is a polynomial mapping of degree 2, often cited as an archetypal example of how complex chaotic behavior can arise from very simple nonlinear dynamical equations. Mathematically, the logistic map is written x sub n plus 1 equals r x sub n parentheses 1 minus x sub n close parentheses, where x sub n is a number between 0 and 1 and represents the ratio of existing population to the maximum possible population at year n, and hence x sub 0 represents the initial ratio of population to maximum population. R is a positive number and represents a combined rate for reproduction and starvation. This figure shows the bifurcation diagram of logistic map. The horizontal axis shows the values of the parameter r, while the vertical axis shows the possible long-term values of x. As can be seen from this figure, with r increasing between 3 and 3.56995, from almost all initial conditions, the population will approach permanent oscillations among two values, then 4, 8, 16, 32, etc. At r approximately 3.56995 is the onset of chaos. at the end of the period doubling cascade. Slight variations in the initial population, yielding dramatically different results over time, a prime characteristic of chaos. Most values beyond 3.57 exhibit chaotic behavior. But there are still certain isolated ranges of R that show non-chaotic behavior. These are sometimes called islands of stability. Since the 1990s, many researchers have noticed that there exists a close relationship between chaos and cryptography. The intrinsic properties of chaotic dynamical systems, such as extreme sensitivity to initial conditions and system parameters, ergodicity and mixing property, naturally satisfy the essential design principles of a critical system, such as avalanche, confusion, and diffusion. The iterative permutation substitution operations suggested by Shannon for secure cipher constructions are widely adopted in chaos-based image ciphers. In the permutation stage, the pixel populations are scrambled in a secret way, which leads to a greater reduction in the correlation among adjacent pixels. In the substitution stage, the pixel values are altered sequentially and the inference of each pixel is diffused to all its succeeding ones during the modification process. With such a structure, minor change in one pixel of the plane image may result in a totally different cipher image with several overall rounds of encryption. Now let's discuss the permutation algorithm in detail. Every preserving chaotic maps, including the cat map, the Baker map, and the standard map, have been widely used in image scrambling. We take the simplest one, the cat map, as an example. The classical honored cat map is a two-dimensional invertible chaotic map described by this equation. The cat map is most easily described in geometric terms. A unit square is first stretched by the linear transform matrix A, and then followed by the modular operation. The above two-dimensional cat map is now generalized by introducing two control parameters, P and Q, as follows. In order to incorporate generalized chaotic cat map into image encryption that operated on a finite set, it has to be discretized, while reserving some of its useful features such as the mixing property and the sensitivity to initial conditions and parameters. The discretized version cat map can be obtained simply by changing the range of xy from the unit square I by I to the discrete lattice n by n, where n is the width and or height of the image. Evidently, the parameters p, q are the immediate candidate for the secret key for permutation. To invert the permutation, we can use the inverse of cat map, which is given by this equation. This figure shows the experimental results. The left-hand side of the figure shows the line test image. The first, second, and third row of the right-hand side of the figure shows the scrambled images obtained by applying the cat map, beta map, and the standard map once, twice, and 3 times respectively. Unfortunately, this kind of permutation approach suffers from two main disadvantages. First, a periodic chaotic map may become periodic after discretization. That is, image randomized by the transformation may return to its original state after a number of iterations. This figure demonstrates the application of the cat map to a grayscale test image with 150 times 150 size. It can be seen from this figure. After 300 iterations, the original image returns. Secondly, these area preserving maps are only applicable to square images. To address these two drawbacks, several approaches have been suggested. For instance, in this literature, the populations of subpixels in each color channel of the plane image are scrambled across the entire color space using a pixel swapping strategy under the control of a keystream sequence generated from the hyperchaotic system. Now, let's discuss the substitution algorithm. The substitution algorithm consists of three major procedures. First, generation of a pseudo-random sequence by iterating a chaotic system. The second, extraction of a keystream sequence from the chaotic sequence. And the third, mixing plane image with the keystream and diffusing the influence of each pixel of plane image to its succeeding ones. Various discrete chaotic maps and continuous chaotic systems can be employed to generate keystream sequences with desired statistical properties, including the most commonly used ones like the Northeastern map, the Lorentz system, the Chong system, and varieties of high-dimensional chaotic systems. In the following discussion, we use the Chong system to generate the keystream for substitution operation. Without loss of generality, it's assumed here that the input is a 24-bit true color image of size h by w. The detailed encryption algorithm is described as follows. Step 1. Arrange the colored subpixels in the input image to a one-dimensional byte array image data in the order from left to right, top to bottom. Step 2. Generate a chaotic sequence of the same length as the image data from Chong system. Step 2.1. Pre-iterate Chong system for n sub-0 times to avoid the harmful effect of transitional procedure, where n sub-0 is a constant. Step 2.2. Iterate Chong system for h by w times. For each iteration, the current values of the three state variables x, y, and z are in turn stored into an array Chong sequence. Step 3. Extract a substitution keystream from Chong sequence according to this equation, where the ABS x function returns the absolute value of x. The sig xm function returns the m most significant decimal digits in x, and the mod xy function divides x by y and returns the remainder of the division, and z sub l is the number of gray levels in the input image. An m value of 15 is recommended, as all the state variables in our algorithm are declared as double precision type. which has 15 or 16 decimal places of accuracy. Step 4. Convert the plain pixel to its cipher form according to this equation, where C sub n and C sub n minus 1 are the output and the previous ciphered colored subpixels, respectively, and this symbol performs bitwise exclusive OR operation. As can be seen from this equation, the modification made to a subpixel depends not only on the keystream element, but also on its previous ciphered subpixel. And thereby, the influence of each subpixel can be spread over all its succeeding ones. For the first subpixel, P sub 0, the initial value C sub minus 1 can be set as a constant. Step 5. Perform several rounds of the overall permutation substitution operations so as to spread the influence of each individual pixel over the entire cipher image. As is known, a good crypto system should resist all kinds of non-attacks, such as brute force attack, statistical attack, non-plaintext attack, and Trojan plaintext attack. Now let's carry out an extensive security analysis to evaluate the discussed image encryption algorithm. The first is the brute force analysis. The main idea of brute force analysis is systematically checking all possible keys until the correct key is found. The key length of an effective crypto system should, therefore, be large enough to defend against a brute force attack over the key space. The secret key of the discussed encryption algorithm is composed of two independent parts: the permutation key and the substitution key, which are chosen to be the control parameters of the cat map and the initial conditions of the chain system, respectively. In the discussed algorithm, the size of the substitution key is far larger than that of the permutation key. So here we only calculate the size of the substitution key. All the state variables in the discussed algorithm are declared as 64-bit double precision type, which gives 53 bits of precision. Therefore, the size of the substitution key is 53 times 3 equals 159 bit. Generally, cryptographic algorithms use keys with a length greater than 100 bits are considered to be computational security, as the number of operations required to try all possible 2 to the power of 100 keys is widely considered out of reach for conventional digital computing techniques for the foreseeable future. Therefore, the discussed algorithm is secure against brute force attack. A fundamental requirement for cryptographic algorithms is that they should be sensitive with respect to secret keys. That is, cryptographic algorithms should ensure that no information about the plaintext can be revealed even if there is only a slight difference between the decryption and the encryption keys. To evaluate the key sensitivity property of the proposed key, the Lena test image is firstly encrypted with a randomly generated secret key, and the resulting cipher image is shown in Figure A. Then the cipher image is tried to be decrypted using 4 different decryption keys as listed in this table, where the first one is identical to the encryption key, and the other 3 have only 1 bit difference from one part of the encryption key. The resulting deciphered images are shown in figures B to E, respectively, from which we can see that an eavesdropper cannot get any information about the play image, even using an almost perfectly guessed decryption key. It can, therefore, be concluded that the proposed algorithm fully satisfies the key sensitivity requirement. The next is frequency analysis. The frequency distribution of cipher pixel values is of much importance to an image crypto system. It should hide the redundancy of plain image and should not reveal the relationship between plain image and cipher image. Histogram analysis is often used as a qualitative check for data distribution. An image histogram is a graphical representation showing a visual impression of the distribution of pixels by plotting the number of pixels at each grayscale level. The histograms of the red, green, and blue color channels of the Lena test image and its output cipher image produced by the discussed scheme are shown in this figure. It can be seen from figures L to N that the pixel values of all the three color channels of the output cipher image are perfectly uniformly distributed over the whole intensity range, and therefore no information about the plain image can be gathered through histogram analysis. The distribution of pixel values can be further quantitatively determined by calculating the information entropy of the image. Information entropy, introduced by Claude Shannon in his classic paper, A Mathematical Theory of Communication, is a key measure of the randomness or unpredictability of information content. The information entropy is usually expressed by the average number of bits needed to store or communicate one symbol in a message, as described by this equation, where x is a random variable with n outcomes, x1 ellipsis xn, and pxi is the probability mass function of outcome xi. It's obvious from the above equation that the entropy for a random source emitting n symbols is the log of n to base 2. For instance, for a ciphered image with 156 gray levels, the entropy should ideally be 8. Otherwise, there exists a certain degree of predictability which threatens its security. We calculated the information entropies of 5 standard test images and their corresponding cipher images obtained by applying the discussed algorithm, and the results are listed in this table. As can be seen from this table, the entropies of all the output cipher images are very close to the theoretical value of 8. This means the discussed algorithm produces outputs with perfect randomness, and hence is robust against frequency analysis. Next, let's analyze the security of the discussed algorithm with respect to correlation between adjacent pixels. For an ordinary image having definite visual content, each pixel is usually highly correlated with its adjacent pixels either in horizontal, vertical, or diagonal direction. However, an efficient image crypto system should procure cipher images with sufficiently low correlation in the adjacent pixels. A scatter diagram is commonly used to qualitatively explore the possible relationship between two datasets. To plot a scatter diagram for image data, the following procedures are carried out. First, randomly select as sub-n pairs of adjacent pixels in each direction from a color channel of the image. Then the selected pairs are displayed as a collection of points, each having the value of one pixel determining the position on the horizontal axis and the value of the other pixel determining the position in the vertical axis. The scatter diagram for horizontally adjacent pixels in the three color channels of the LiNA test image and its output cipher image are shown in figures A to C and D to F, respectively. Similar results can be obtained for the other two directions. As can be seen from figures A to C, most points are clustered around the main diagonal, whereas those in figures D to F are fairly evenly distributed. The results indicate that the proposed scheme can effectively eliminate the correlation between adjacent pixels in a plane image. To further quantify and compare the correlations of adjacent pixels in a plane image and its output cipher image, the correlation coefficients for the sampled pairs are calculated according to the following three formulas, where xi and yi are grayscale values of the ith pair of neighboring pixels, and n denotes the total number of samples. This table lists the calculated correlation coefficients for adjacent pixels in the LiNA test images and its output cipher image. As can be seen from this table, the correlation coefficients for adjacent pixels in the output cipher images are practically zero. The last one is plaintext sensitivity analysis. To be robust against Trojan plaintext attack, a cryptographic algorithm should be sensitive with respect to plaintext. A Trojan plaintext attack is an attack model for cryptanalysis, which presumes that the attacker can obtain the ciphertext for arbitrary plaintexts. As is known, a Trojan plaintext attack is more powerful than non-plaintext attack. This is because the attacker can directly target specific terms or patterns without having to wait for these to appear naturally, allowing faster gathering of data relevant to cryptanalysis. Therefore, any cipher that prevents Trojan plaintext attack is also secure against non-plaintext and ciphertext-only attacks. Differential cryptanalysis is the most powerful Trojan plaintext attack that analyzes how the differences in two plaintext messages affect the differences between the corresponding ciphertexts. To do this, an opponent may firstly create two plain images with a slight difference, and then encrypt the two images using the same secret key. If some meaningful relationship between the plain image and the cipher image can be found by comparing the two cipher images, the secret key may be determined with the help of some other analysis methods. Obviously, this kind of cryptanalysis may become impracticable if a slight change in the plain image can be effectively diffused to the entire cipher image. That is, changing one bit of the plain image affects every bit in the cipher image. The diffusion effect of an image crypto system is usually measured using two criteria, that is, NPCR, the number of pixel change rate, and UACI, the unified average changing intensity. The NPCR is used to measure the percentage of different pixel numbers between two images. Let I1 IZK and I2 IZK be the IZ pixel in case color channel of two images I1 and I2, where K equals 1, 2, 3 denotes the red, green, and blue color channels respectively, and H and W are height and width of the image. The NPCR and the UACI are defined as the following two equations. It can be derived from the above two equations that the expected NPCR and UACI values for two truly random images with 256 degree levels are 99.609% and 33.464% respectively. To evaluate the worst-case diffusion performance, we randomly choose a pixel in each of the 5 test images and change its least significant bit, as is illustrated in this table. The two images in each test pair are encrypted using the same secret key, and their NPCR and UACI values are listed in this table, from which we can see that the discussed scheme takes a minimum of 2 and 3 encryption rounds to achieve an acceptable and a desired diffusion effect, respectively. I have now come to the end of my speech. In summary, the chaos-based image encryption technique provides an optional trade-off between security and efficiency. It has shown to be a promising way for online secure image communication applications. Thanks for your attention.